Hello everyone, and welcome to the video on for section 5.5, bases other than e and the applications. What we're really going to be doing is looking at the calculus involving things that are, instead of e to the x, like 7 to the x, or log base 4, how we deal with those, because those are all smooth curves, and therefore they do have a derivative, and we're going to be asked to find those. And also, we'll also be looking at some integration as well. The objectives for this particular video: 1, define the exponential functions that have bases other than e. Differentiate and integrate exponential functions with bases other than e, and also we'll include the logs as well. And then use exponential functions to model compound interest and exponential growth. To start out with, we're going to deal with two definitions. We're going to define what an exponential function of base a is, and also what the log function is when it's log base a. So, start out with, if a is a positive real number where a does not equal 1, and x is any real number, then the exponential function to base a is denoted by a to the x, and is defined by a to the x equals e raised to the natural log of a times x. Notice that the x is not inside the natural log function. It is the natural log of a is a coefficient, if you will, to the variable in that exponent. And that's going to be key when we look at that the definition of this particular function. Now let's look at the definition for a logarithm function to base a. And again, if a is a positive real number, again, a does not equal 1, and x is any positive real number. Remember, we cannot take the log of anything of 0 or of a negative number, so x has to be positive. Then the logarithmic function to the base a is denoted log base a of x, and is defined by log base a of x equals 1 over the natural log of a times the 1 over the natural log of a times the natural log of x. Now this one right here should be somewhat familiar to you, because this really does give us, this is where the change of base formula comes in. If you remember last year, we had the change of base. And the change of base formula said that log base a of x equals the natural log of x over the natural log of a. Well, it could be any base. Some of you used log of x over log of a, but this one right here, remember, it could be, we could use any base we wanted, and we're going to choose to use the natural log on this case. So we know you need to keep in mind that log base a of x is equal to this. Now again, it's important to remember that the natural log of a here, that is a constant value. So this is really just a constant times the natural log of x. And that will be something that we'll take a look at once we get to the calculus, to how to find the derivative of this particular function. Now let's go and derive the derivative formulas for these two functions, the a to the x and log base a of x. So I know in this case that a to the x is e raised to the natural log of x. And you need to remember that we have defined that the derivative of e to the x is itself. So when I take, in this case, when I want to find the derivative with respect of a to the x, I need to take the derivative with respect of e raised to the natural log of a times x. Well, I know that this particular derivative is equal to e raised to the natural log of a times x times the derivative of the inside function. Now my inside function is the exponent, and since the natural log of a is really just a coefficient on that x, the derivative of the natural log of a times x is just going to be the natural log of a. And so this function becomes e raised to the ln a times x is just a to the x ln a. So with this, I can now say that the derivative of a to the x is just going to be a to the x times the natural log of a. That's one of our new derivative formulas. And then the derivative with respect to x of a to the u is going to be a to the u times the natural log of a times du dx. Now let's take a look at the derivative for the log base a of x. In this case, I know that's going to be the derivative with respect to x of log base a of x is going to be equal to the derivative with respect to x of 1 over the natural log of a times the natural log of x. Well, in this case here, remember again, as I mentioned before, that the 1 over the natural log of a is just a constant. So this is just going to be a constant times the derivative of ln x. And we know that's equal to 1 over the natural log of a times the derivative of ln x, which is 1 over x. Or we get that this is 1 over x times the natural log of a. So with this, I am able to say that the derivative of the natural log of a, log base a of x, is equal to 1 over x times the natural log of a. And if I take the derivative of log base a of u, it is going to be 1 over u times the natural log of a times du dx. So with this, we now have 4 new formulas that you should be familiar with. You should be familiar with that the derivative of a to the x is a to the x ln a, the derivative of a to the u, derivative of log base a of x, and the derivative of log base a of u. Those should be committed to memory. Now let's take a look at just a couple examples. In this first example, we're going to take the derivative with respect to x of 3 to the 4x power. Well, I know that the derivative from before, I know that the derivative with respect to x of a to the u, is equal to a to the u times the natural log of u times du dx. So in this particular problem, I know u, if you will, is going to be 4x. I know a is in the 3 spot. So the derivative with respect to x of 3 to the 4x is going to equal 3 to the 4x times the natural log of 3 times the derivative of 4x, which is 4. So I will get this equal to 4 ln of 3 times 3 to the 4x power. I may have made a mistake there, it looks like it. This should be natural log of a right there, not natural log of u. I don't know why I have that. But anyway, the next one, the derivative with respect to x of log base 2 of x squared minus 3x to the 3rd power. One of the things I'm going to do with that particular problem is I'm going to rewrite that. I'm going to say that's equal to, because of the log properties, that 3 can go out in front. So that's going to be the derivative with respect to x of 3 times log base 2 of x squared minus 3x. And now when I take that derivative, again, using that property that we just had, I know that this derivative is going to equal, for this problem, that derivative is going to equal 3 times 1 over the x squared, the u, minus 3x, times the natural log of my base, which is 2, times the derivative of the inside function. So that's going to be 2x minus 3. Or I am going to get 6x minus 9 over x squared minus 3x times the natural log of 2. The last part of this video is really looking at the compound interest formulas, just refreshing your memory with those because we will be using those, as well as the idea of an exponential growth or decay model. In these cases here, remember what's important on these formulas is remembering what each letter stands for. I know that P is my initial amount. It's often, when we're talking about compound interest, it's often called the principal. But it is initially what we're starting out with. When you're dealing with compound interest, T is time in years, but in other situations, T can be in seconds or minutes or hours or whatever it happens to be. A is the amount that you end up with after t years in compound interest, or whatever is after a particular time period. R is your interest rate, or your growth or decay rate. And N is the number of compoundings per year. Now this one really applies to just one of the formulas because this is where we're going to be adding in the interest a fixed number of times instead of interest being compounded continuously. So when we have interest being compounded n times per year, we have this formula. A equals P times the quantity of 1 plus R over N raised to the NT power. And if we are compounding continuously, we have A equals PE to the raised to the RT. Now what's important to remember as well is that there will be times when we're looking at growth or decay models. And when we're looking at growth or decay models, what we're really dealing with in that situation is another application of that particular formula. The P and the units might be a little bit different in terms of the time and what we're working with. We may not be working with money. Maybe we're working with bacteria growth, or actually even looking at what happens when a certain antibiotic is applied to a bacteria. So in that case, bacteria decay. So when we look at an exponential model, it will really be looking at a form of the PERT formula. So with that, I hope this does conclude this video. I hope you're doing well, and we will see you in the next class.